Alrighty, welcome to the last section of Chapter 4, 4.6, Determinants and Cramer's Rule. Now, I know by now most of you will probably hate me because of row ops, and if you've been struggling with row ops and solving via row ops, you're going to absolutely love today. Because what we're going to talk about today, like I said, are determinants and something called Cramer's Rule, and they're basically going to be the sixth method for us solving systems of equations. And they throw row ops out the window. They are so much easier. I've been waiting for this day. I love determinants. They're so easy to do, and they make row ops pretty much obsolete. So if you've been struggling with row ops today, you're going to like today. So let's start with what a determinant is. Like I said, we've been talking about row operations and being able to convert stuff and all that jazz, which is great, but there's something else called a determinant that helps us find inverses much easier and helps us solve much easier. So a determinant's kind of hard to define exactly what it is, because what it is just a number. It's a number. It's a number that you create from a matrix. It's created from a square matrix. The only determinants we're going to solve are for 2x2s. There's a beautiful way that they solve a 3x3 in your book, and you're more than welcome to take a look at that, but for our purposes, we're going to stick with the 2x2 because they are very, very straightforward. So a determinant is solved like this. If you have a matrix with entries A, B, C, and D, then your determinant is A times B minus B times C. That's it. You basically take the diagonals and you subtract them. That's all you need to do. So let's see if we can find the determinants of these 2x2 matrices. So we've got this one here. We're working with something very similar last time. It's a 2x2 matrix of -3, -1, -3, 4, and -2. And notice, if you'll notice very carefully, on the sides here, these are no longer those brackets, right? They're not the brackets, and that wasn't intentional, or that was intentional. That wasn't me just, not knowing where the bracket was on the note packet. It's actually different. When you have the absolute value bars around a matrix, you are specifically saying, I want to find the determinant of this matrix. So that's some way you might see it. Some people might say, find the determinant of, and then they'll show you a matrix, or they'll just change those to bars. If they change those to bars, it's actually asking you to find the determinant, okay? So let's go ahead and find that determinant. We're going to take this diagonal, we're going to multiply it together. So -1 times -2, and then we're going to subtract it from this diagonal. Well, I'm not going to use that green. This diagonal, okay? So subtract it from -3 times 4. Now, the only thing I would caution you about is that this is very similar looking to when we multiply matrices, right? So don't mix these two up. Don't think when you multiply matrices you deal with the diagonals at all. Think determinant, diagonal. Determinant, diagonal. Notice there are no D's in the words matrix multiplication. So the only time you use the diagonal is when you want to use the determinant, okay? But other than that, it's virtually the same. So let's multiply this together. We get 2 minus -12, and so our determinant is 14. That's it. That's our determinant. And not very useful right now, but that's how you find it, right? It's going to be very useful in just a sec. So let's try one more. I encourage you to try this one on your own. Try to find the determinant of this matrix. Go for it. Alright, so I hope you had a chance to try. I hope you paused the video. If not, please do so now. But let's go to diagonal by diagonal. So, -4 times 3 minus 6 times -2. We end up with -12 minus a -12. The determinant here is equal to 0. And that's awesome. Cool. We found it. That's going to mean something later on. Right now, it just means that the determinant is 0. Okay. So as you can see, the determinant, very, very easy to find. It's just an algorithm, right? So it's just an equation that we plug into. You just subtract the diagonals. Where this is useful is in finding the inverse of a matrix. So like I said, you're going to really like today because it gets rid of row ops. We no longer need row ops to find a determinant. Now just be careful, this section is not covered in your textbook, so if you have any questions on this for the homework, you need to make sure you refer to videos or to these notes, okay? When you defined the inverse of a matrix, last time, we set it up so that you had the original matrix times the identity matrix, right? Or augmented with the identity. And then you had to go and solve it, and you ended up with I and A inverse. And if you liked that way, that's absolutely fine. But there's a much easier way to find this inverse. Instead, if our matrix is that same A, B, C, D, right, so any 2 by 2 matrix, then our inverse is going to be this formula here. We'll find our determinant. Remember, determinant's just a number. We'll flip it, and we'll multiply it by this new matrix. So it's a lot more algebra instead of row operations. So let's take a look at that. There's one spelled out here for you, but why don't we just jump down to the first one, where we find the inverse of this matrix. Let's find the inverse here. So the first thing we're going to need, we got to remember, okay, so the inverse is equal to, so A inverse is equal to 1 over the determinant times this new matrix. And this new matrix is D, negative B, negative C, A. And we'll talk about what that means in just a sec, but let's start with the determinant part. Let's find, okay, what is the determinant of A? Oh, darn it. I was trying to avoid that. Okay, so what is the determinant of A here? Well, remember, determinant means diagonals, so we're just going to take those diagonals, we're going to multiply them, and then subtract them. So we've got 0 times negative 5 minus negative 1 times positive 1, right? So we get 0 minus a negative 1, or 1. We end up with 1 as our determinant. Fabulous. What is 1 over 1? So now instead of just the determinant, we need 1 over the determinant, which would be 1 over 1, or just 1, right? So it looks like we're multiplying by 1 to this matrix here. Good, awesome. So now we need to create, the last thing we need to do, so this is step 1, here was step 2, and lastly, let's do step 3. We need to create this new matrix that we're going to multiply by 1 over our determinant. Now remember, our original matrix was A, B, C, D, right? So it went straight across the rows A, B, and then row C, D. So that's what they're coordinating to here with this new matrix. What they want us to do is take A and D, and they want us to switch places, right? So what that looks like here is if A is negative 5 and D is 0, then we're going to switch their places, 0 and negative 5. That's what they mean by A and D. Now for B and C stay in their respective areas, but now they're the opposite version. So we're going to take the negative 1 and the 1, we'll make it positive 1 and negative 1. So we didn't switch them, but we changed their signs. And we have this new matrix. 1 times all of these guys, a scalar multiplication, right? So we distribute a 1 in. That's not really going to change anything. So our inverse is 0, 1, negative 1, and negative 5. And that's it. That's our matrix. Guarantee you multiply that, you will get the same thing. If you went the row op route, you would get the same thing. And if you multiplied it by our original matrix, you would get the identity. Let's try it again with B. Now I encourage you to pause the video here and try it out on your own. Try to multiply this one and use that formula to determine the inverse of this matrix in B here. So go ahead and pause that. Use the determinant to find the matrix. Alright, so let's do it together. Hopefully you've had a chance to try it out. So we're going to start step 1. We're going to need that determinant, which means we subtract the diagonals. Well, 3 times negative 2 minus negative 6 times 2 is going to be negative 6 minus negative 12, or negative 6 plus 12, which would be a positive 6, right? So this time our determinant's not 1, not as pretty, but that's okay. That's okay. All right, the next thing we're going to do is we're going to need to take that determinant and we need to flip it. So that would be 1/6 instead of 6, right? And then lastly, we will take that 1/6 and we're going to multiply it by that special new matrix, right? So that special dA negative B negative C thing. So we'll go back here. We're going to switch A and D. So you have -2 and 3. And then we're going to negate the other two. So we're going to change the sign 6 and -2. Lastly, let's multiply in that scalar, right? Let's multiply it in. So we get -2 over 6, or 1/3. 6 over 6 is going to be a 1. I'm sorry, a -1/3. And then we get a -1/3 again, and a 1/2. Oopsies. And then we'll close out the matrix. And we end up with our inverse. -1/3, 1, -1/3, and 1/2. And look at how little work that was, right? So little work for such a important concept, being able to find that inverse. So now if we wanted to go solve a system, what could we do? We could take that inverse and multiply it by b. Notice it's like 3 less steps. Like, not even. It takes 3 steps. It takes like 5 less or something like that. So this would be our inverse. This would be our B inverse. All right, let's do it one more time. We're going to do it with C down here. We'll kind of just section this off. Awesome. So C is 0, 4, 0, 4. Can you already kind of sense what's going to happen here? Can you already kind of sense about an inverse, about a special case maybe? Can you kind of see these things that maybe they're the same, right? So I don't think this one's going to work, right? This matrix probably doesn't have an inverse. Because remember, matrices that have inverses can be solved for a system, right? We can go all the way back to elimination. But this isn't, I don't think this is going to work because it's the same thing. But let's see what happens. Let's see if, maybe we didn't notice that. What would happen with this determinant method? So let's start by finding that determinant. Determinant of, we'll call it C, not A. Determinant of C would be 0 times 4 minus 0 times 4, right? So the diagonals, and we end up with 0 minus 0, or 0. All right, determinant is 0. Okay, step 2, we need 1 over the determinant of C. Hold up there, dudes. Is that legal? Can I say 1 divided by 0? Am I allowed to say that? No, right? So this is not a real number. So there's no way I can multiply it into a new matrix to get an inverse, right? So if your determinant is 0, you've already figured out that it is one of those cases where there is no solution. And that sucks, right? So this would be no inverse. But notice it took like 3 less seconds. It took like 20 less seconds to figure that out than it did with row ups. So if your determinant is 0, you do not have an inverse. If you have any questions about this, being able to find a determinant using, finding an inverse using a determinant, go ahead and pause the video now and ask any questions you may have. Oh, and I know you're all wondering, no, I am not going to make you do both. I make you do both on the homework so that you realize one you like, but on the test, you may use either method you prefer. So row ops or not, it's entirely fine with me. I much prefer this way. I think it's much easier, and I just don't see the reason for making you do something that a computer does anyways. So now that you know both, pick your favorite. If this was total gibberish to you, though, and you're like, what the crap is a determinant, then maybe you want to go with the row ops, and that's fine too. Alrighty. The last thing we're going to talk about today is something called Cramer's rule, and it's going to be our so we have graphing, substitution, elimination, augmented matrices. We have the matrices with the inverse and row ops. We now have matrices with the determinant and the inverse. And so Cramer's rule is going to be our 7th method. 7 methods for solving a system. So it's going to be our 7th method, and I honestly think you guys are going to like it the most because it involves determinants up the wazoo. That's really all it is it's a bunch of determinants. So there is a beautiful explanation of where Cramer's rule comes from in your textbook. I highly recommend you look at it. But for the interest of time, we're not going to talk about how it came about. We're just going to talk about using it. But if you are ever bored or maybe can't fall asleep, then definitely look at this beautiful explanation of Cramer's rule. It's on page 220. It's on page 220 if you ever want to check that out. 220. To geeks like me, it is a mosaic. Anyways, so let's take a look at this rule, right? So this rule makes 3 different kinds of determinants. It's got 3 determinants. We're going to call them d sub x, and d sub y. And we're going to talk about how those 3 are created in just a sec. But just know that there are 3 separate determinants. And because they're determinants, they're numbers, right? They're just numbers. It's a number at the end of the day we're talking about, like a 2 and a 5 and a 6, okay? So we're going to have 3 determinants. They come out of this sort of setup. Now this may look a little strange to you, but if you look closely, it's just standard form. ax plus by equals c. And it's happening twice. The first time it's got all subscripts of 1, the second time it has all subscripts of 2. So these are just our standard forms. Standard forms. Remember those way back when? Standard form, right? When you have these standard forms, we're going to create some determinants from these standard forms. So let's take a look at this first one. This first one is just d all by itself, right? This is a determinant that comes out of the coefficients of the left-hand side. So this is the a's and the b's, the a's and the b's. That's what this determinant is. So I know it looks fairly complicated with all these a1s, b1s, but don't panic, right? It's the same matrix you would make from the left-hand side of the equation. So we'll just call this the left-hand side. Coefficients. Okay? That's what this matrix is. And then you make a determinant out of it. So you just do the diagonals, and that's what you get, right? Whatever that number is, it ends up being like 6 or 0 or whatever. That's our first matrix. That's just the d, right? It has nothing to do with x and y. It's just d, right? In fact, it's both. The second one we will call d sub x, and it's everything it's all the coefficients that don't involve x, and that's important. The coefficients that are not attached to x. Not attached to x. In other words, they're the b's and the c's. So if we look back at our original one, we know that the a's were always attached to the x's. And so this matrix is made of, this matrix that we eventually turn into a determinant is made of all the b's and the c's. So we're taking the determinant of a matrix of the b's and c's. All right, we'll come back to what to do with that in a sec. But the third one is, you guessed it, if dx is a matrix made of all the stuff that's not x, then dy is a matrix of all the stuff that's not y. Right? So in our y, our original form, y had all those b coefficients, and so there are no b's in our y matrix. It is a's and c's, right? So a1, c1, b, a2, c2. It's the x coefficients and the constants. And then we make a determinant out of that. We just multiply the diagonals. We end up with 3 different numbers. All right, cool. Now, in order to solve using Cramer's rule, we have these 3 determinants, right? These 3 numbers. They're just numbers. We're going to divide. That's it. Once you have these 3 numbers, you divide. Divide dx, that one you made with no x's, divided by d, the one you made where it has everything. Same thing goes for y. If you want y, take dy, the stuff that has no y's, and divide it by d, the stuff that has everything. And as it's presented here, it looks incredibly complicated. It looks like you're going to be sitting here for 45 minutes plugging in all these numbers. But remember, you've already made 3 numbers. So it's going to take about 15 seconds from this point. Let's try that out. So let's try that out. I know I've said a lot of stuff here about d's and y's and determinants and all sorts of crap. But again, it's always easier when you see some numbers. So go ahead and scroll down, or go to the next page probably, and you'll see the Cramer's rule reminder, right? If you're solving for x, you take dx over d. For solving for y, you take dy over d, right? And just as a reminder, we put up at the top there, but let's take a look at this matrix, or this system, right? So we have this system. 5x plus 7y equals -1, and 6x plus 8y equals 1. All right, the first thing we need, let's solve for x. Let's find our d and our dx. and our dy. So we need those three. And remember, those are going to be numbers at the end of the day. First, we got to set up a matrix so that we can find the determinant. So the d, remember d with nothing attached to it, is just going to be our left-hand side. So let's go take a look back at our system. What 2 by 2 would we create out of the left-hand side, right? You guys are really good at this. You're always good at creating these matrices out of these coefficients. So if I just want the left-hand side, my matrix is going to look like 5, 7, 6, and 8, right? That's it. That's the matrix we need. Now, in order for us to call it a determinant, right, we wouldn't want to draw these brackety guys. We want to draw the lines. That way we know it's a determinant. But that's the matrix we're going to start with, this matrix on the left-hand side. Let's go ahead and find the actual number that would be the determinant. So let's take those diagonals. Take those diagonals, and we'll subtract them. So d is equal to 8 times 5 minus 7 times 6. In other words, 40 minus 42, or negative 2. All right, it looks like d is negative 2. That's the first number we have. Awesome. D is equal to negative 2. Any questions on that? Go ahead and pause the video and talk about it. Second thing we want to do is find dx. Now remember, dx means all of the coefficients that aren't attached to x, right? So it's kind of an opposite trick kind of game, right? X is the part that you get rid of. So the matrix, or the determinant we want to find here, let's do it in red, is going to be all the stuff that doesn't have an x attached to it. So not the 5 and not the 6, but everything else. 7 and an 8 go with the y's. And then a negative 1 and a 1. Those are those b's and c's we were talking about, right? So we've got our second matrix, and we're going to make it into a determinant. So d sub x is equal to 7 times 1 minus 8 times negative 1. Times. Here we go. So 7 minus negative 8. It's going to be 7 plus 8, right? Or 15. Fabulous. So we got 15. And that will be d sub x. Alright, there's our second determinant, our second number. Let's do the same thing with y's. This time we'll make it, I don't know, purple. Let's do the same thing with y's. Remember, everything that's not a y. This one can be a little trickier because it's not going to be just the left-hand side or the right-hand side. We got to kind of ignore that middle part because that's where the y's sit. So it's going to include the 5 and the 6 because those don't have y's on them. It's not going to include the 7 and the 8 because those are attached to the y's. But it will include the constants negative 1 and 1. All right, let's find that determinant. So we've got that matrix now. This is all the stuff that's not y, right? Find that determinant, we end up with 5 times 1 minus 6 times negative 1. And we end up getting 5 minus negative 6, or 11. So dy is equal to 11. All right, we found our three numbers, our d, dx, and dy. Any questions on those, stop the video now and make sure you get them answered, okay? The very last step is to find x. Let's do it in, now let's do it in red. Now let's do it in orange. I'm very indecisive about my colors today. So x is going to equal dx over d, which again, up here, looks like a whole bunch of work, right? But now we know dx and d are just two numbers, so we can plug them in. That equals 15 over negative 2, or in other words, x equals negative 15 halves. There. X equals negative 15 halves. Easy peasy lemon squeezy. Let's do the same thing for y. We'll do this one in green. Y is going to be equal to dy over d. In other words, it's going to be 11 over negative 2. And so it equals negative 11 halves. And we have our solution. Our solution to this horribly complex problem is the nice and easy negative 15 halves, negative 11 halves. You see how easy that was? How many people love Cramer's rule? Because it just comes down to three numbers and then you divide. That's it. That's all it was. Alrighty. Go ahead and try out this next problem on your own. Try it out, see what happens. Use that Cramer's rule. Use Cramer's rule and see if you can figure out those 3 determinants and then what you need to subtract in order to get the solution. Go ahead and try it out now. Pause the video so you have plenty of time to try, and then we will do it together in just a sec. Alrighty, hopefully you've had some time to try. I'm going to go ahead and do this one. If you didn't, then I really hope you're extremely good at another method and you're at least going to try for the homework tonight. But if you have, hopefully you got the same answer I'm going to get. Alright, so I'm going to start with my D matrix, my D determinant. That's going to be stuff that's all over here, all the right-hand side. It's going to be 2, -3, 3, and 4. That's that determinant. I'll take the determinant of that matrix there. 4 times 2, so I'm doing 4 times 2 minus -3 times 3, right? So 8 minus -9, or 17. 17, fabulous. Alright, so I got D is equal to 17. I'll put that there, remind myself. Now I need dx. Dx we'll do in pink. Remember, that's everything that would not that would not be a coefficient of x. So I can kind of blur that out so I can see. And that would be, let's see, all the stuff on the right-hand side. So -3, -26, 4, and 12. Determinant of that, it's going to be 12 times 3 minus -26 times 4. Alright, so we end up getting 36 minus 6 times 4 is -104. That's going to equal positive 140. So dx is equal to positive 140. Sweet. Alright, moving right along. We've got dy. Everything that's not a y, right? So this one is kind of the 50-50. So I'm going to need all the stuff on the left-hand side and all the stuff on the right-hand side. So 2 and 3, -26, and 12. Alright, and then the determinant of that's going to be 2 times 12 plus 3 times -26. And that's going to equal 24 minus 78, or -54. Alright, so dy is -54. Last but not least, I need to find x and y. I'll do that down here. X is going to be dx, so pink over d, 140 over 17. Since 17 is prime, it is not going to reduce, right? 17 is prime. And, just one second. Where did I get this problem? Okie dokie. Okay, and then y is going to be -54 over 17. 54 divided by 17 is not a whole number as well, so that is our answer. Alright. I hope you got the same thing. If you didn't and you noticed I made a mistake, please someone send me an email. But that sounds like about the right answer, right? So it's got this weird problem, and it looks like Cramer's rule is the fastest way to solve that. Alright. Very last note on the bottom here. It's very important. As with every single one of our other methods, sometimes it doesn't work, right? And that sucks. Sometimes it just doesn't work, no matter what method you have, whether you have graphing, substitution, elimination, matrix with augmented, matrix with inverse and row ops, inverse and determinants, whether you're using Cramer's rule, whether you're using any of the 7, there's always ones that don't work because you've got parallel lines or the same line, right? How that presents itself in Cramer's rule is when your d equals 0. D cannot equal 0. Now be super careful about that. I did not say anything about dx. I did not say anything about dy, right? Those would have solutions of 0. But when d is equal to 0, what's going to happen? Well, you're going to try and find x equals dx over d, and you're going to get something like 17 over 0. And why is that a problem? Because you can't divide by 0. Eek! Eek! You can't do that. So if you end up with a d equal to 0, your right-hand side, just like when we were looking at this problem C up here, right? When we were looking at C and our determinant ended up being 0, we couldn't find it because there was no inverse. Same thing goes with Cramer's rule. We can't divide that d out, right? We can't divide that determinant. So it doesn't work, and it has no inverse, and therefore it's an inconsistent system. We can just claim that right then and there. It is an inconsistent system. That's it. All right. That actually closes out Chapter 4. We've talked about a whole mess of a bunch, right? So we will have a review day soon. Your homework for 4.6 will be due next time, and then after that we will have our Unit 4 test. If you have any questions at all, because there's a lot of ways to solve these systems, then please, please, please get them answered as fast as you humanly possibly can, because the Unit 4 test will ask you to do some of these, and there's a lot of stuff we've talked about. It's one of my most favorite chapters, but it is also one of the most complicated. So if you have anything you need to discuss with me, I'm always available by email. Just give me 24 hours to respond. And if you need to, you can talk to the sub, you can come to after-school tutoring, you can talk to peers, friends, you can consult homework, videos, notes, anything that you may have, textbooks. Please recall that there are a couple sections in here that are not actually in your textbooks, but there are many, many resources for you to use. As long as you use them, you will be okay. So if you have anything, just let me know. Otherwise, feel free to start your homework, and we'll see you for the unit test.